Okay, today we'll cover Bayes' theorem. The purpose of Bayes' theorem is pretty simple. We know what is the probability of A given B, and we want to know what is the probability of B given A. That's it. That's the purpose, the main purpose of the Bayes' theorem. We know that probability, this is called a prior probability, and this is called posterior probability. And your book covers an example. So let's do exactly the same example as in the book. We have two events. These two events are mutually exclusive and collectively exhausted. So, and they are called A1 and A2. A1 is the event that it rains tomorrow, and A2 is the event that it does not rain tomorrow. Okay? So these events are mutually exclusive and collectively exhaustive. So it means that either it rains or it doesn't rain. That's it, no more. And if it rains, it doesn't rain. Okay, so they are collectively exhausted and mutually exclusive. A1 and A2. We have another thing that is called whether or not rain was predicted. Okay, we have the weatherman and whether or not the rain is predicted or not. So we may have this prediction that it rains tomorrow, or it may not. Okay? So, and for example, the probability that it rains is equal to 0.5. That came from historical data. So 25% of the time it rains. So the probability that rains is 0.25. So the probability that doesn't rain is what? 0.75, because these are mutually exclusive and collectively exhaustive. Okay. And they know that the probability that is predicted, or B, if you will, that the rain was predicted and it rains is equal to 0.85. So we have a good waterman. Okay? It predicted pretty good. It was predicted and then it rains 0.85, 85% of the time. And what is the probability that it was predicted, given that it doesn't rain? It was predicted that it was going to rain, but it didn't rain. That is 0.20. How come? Well, these two things shouldn't be equal to 1. And I'm going to show you why. If you develop the 3 diagram, it is either rain or doesn't rain. So either A1 or A2. Okay? Now, if it rains, we have the probability of being predicted or not predicted. Predicted or not predicted, right? So the probability that it was predicted, given that it rains, is equal to what? 0.85. So what is the probability that it's not predicted, given that it rains? So this is the other point 15. Okay? The probability that it was predicted given that it didn't rain or it doesn't rain is equal to 0.2. So this branch over here has to be 0.8. Okay? So that is why these 0.85 and 0.2 are the differences. Okay? So don't be confused about that these two events has to be 1.0 when you add them up. Don't have that misconception about the prior probabilities. So, going back to this one, the probability that it rains is what? 0.25, that it doesn't rain is 0.75. So at the end, the probability that rains and that is predicted is equal to what? 0.25 times 0.85. 0.85 times 0.25 is equal to 0.2125, and then this one is equal to 0.25 times 0.15, and this one is 0.75 times 0.2, and so on. And at the end, all these probabilities has to be equal to what? To 1. Because in a tree diagram, at the end, all the probabilities has to be equal to 1. Anyways. And so the probability that it didn't rain, but it was predicted, is equal to what? 0.2 times 0.75. This is equal to 0.15. Okay, this one, the probability that it didn't rain or doesn't rain, and it was predicted, is equal to 0.15. Okay. So based on that information, we would like to know what is the probability that it will rain tomorrow, given that it was predicted, which we don't know. We know these probabilities. We know the probability of B given a 1 and B given a 2, but we do not know what is the probability that it rains A1 given that B. So it's the inverse. And for this one, we are going to use a Bayes theorem. Okay? So the general formula for the Bayes theorem is on page 167, is 413. And it says that the probability of AI given B is equal to the probability of AI times the probability of B given AI divided by the probability of A1 times the probability of B given A1 plus the probability of A2 times the probability of B given A2 plus so on, the probability of A sub n times the probability of B given A sub n, where again A's are all these mutually exclusive, and the A's are mutually exclusive and collectively exhausted events, right? So A's are the mutually exclusive events. It's either rain or doesn't rain. Okay? Or it may be that you are either Hispanic or Caucasian or African American or Asian American. Those are the 4 possibilities, or other, if you will, or 5 possibilities. Okay? So these are the A's. A's are the events that are mutually exclusive and collectively exhaustive. And this is the formula for that. So if you see the tree diagram, what you are saying is that at the end, what is considered is since you are getting the probabilities of being predicted, the only two ways in this case that the rain was predicted are these two branches. So these branches are going to be my universe, if you will. Okay, so going back to this one, what is the probability that it rains given that it was predicted? What is the probability? I don't know. I know what is the probability that it was predicted given that it rains, or it was predicted given that it doesn't rain. It's given in the problem, but we don't know what is the probability that it rains tomorrow when it was predicted. So let's do that, and let's use this this formula over here. This B given A. Okay, we have the probability that it rains, given that it's predicted. It should be equal to the probability that it rains times the probability that it was predicted, given that it rains, divided the probability that it rains times the probability of predicted times given that it rains, plus the probability that it didn't rain times the probability of being predicted given that it didn't rain. What? Very confusing, but that's the way it is. Guys, but it's, I mean, if you, after this, I'm going to do another problem. So, it's equal to what? It's really equal to 0.2125 divided by 0.2125 plus 0.50. You see? Which is these probabilities. The probability that it rains times the probability that it was predicted when it rains is 0.85, so it's 0.25 times 0.85 is 0.2125, and the other one is this one is 0.25. So the only, if you see the tree diagram, the only way that it predicted, it was predicted that the weather, the rain, there were these two branches. In the other two branches, in this one, it wasn't predicted, and in this one, it wasn't predicted the rains. Okay? So we need to use the branches where the rain was predicted because it's the given that it was predicted. That's what I want to know, given that it was predicted. What is the probability that it rains given that it's predicted? Okay, so it has to be 0.2125 divided by 0.2125 plus 0.15, and that probability is equal to, where's my plus 0.15 x times equal to 0.59. So if the waterman predicts that it will rain, the probability that it's going to rain tomorrow is 0.15. Okay? Based on the theorems, the base theory. Okay? So we know what is the probability of B given A1 and the probability of B given A2. But we don't know what is the probability of A1 given B. So that is the purpose. That is the only purpose of the Bayes theorem. And we will have one of these in the test.
Oh.
Absolutely. It's a fact. Probability equal to 1. Okay? I mean, the formula is in your book. You don't need to write down this formula. Let's do one of the problems.
4.14 sounds good to me.
What? No, the 4.14 is homework. So let's do this one that is more interesting. Really. So believe me. And you don't have the answers in the back of the book. So with this one, and just think about it. Really, think about it. Even if you create your own tree diagram, you will see that it's easier to get these terms. Okay, let's do 429. 429 says, Super D is a major video distributor that purchases blank DVDs from two sources. So they have two sources. Disc maker, okay, they have two sources. Disc maker that provides 62% of the DVDs, and media supply that provides the remaining 38% of the DVDs that they use. So this is a company that has two suppliers, only two. So these are the mutually exclusive events and collectively exhausted. Because of what? Because either come from DM or disc maker or from media supply. Okay? And this maker gives the 62% of all the DVDs that come to my company come from this maker, and the other 30% are from media supply. Okay. Historically, 3% of the DVDs has purchased from this maker has been defective. So this maker is 3% defective. And 2% of the discs from media supply are defective. Okay, check the numbers. Check the numbers and tell me, why do you think that this company gets the majority of the DVDs from a supplier whose defective rate is higher? It's 3% versus 2% of defective from the media supply.
You're getting a greater percentage.
What?
You're getting a greater percentage from it.
Yeah, it should be cheaper. Should be cheaper. I mean, I wouldn't use, if they were the same price, I wouldn't use more supplies from a supplier that has more defective products. Or the supplier, the media supplier, do not have the capacity to fulfill my needs. I mean, either one of those, right? So the fact is that we have two suppliers, and those two suppliers give us this. Okay? So we know that the probability that is defective given that comes from DM is what? 0.03. That is the probability. That's what the problem is telling me. That is defective given that comes from supplier data media. This maker. From this maker, the probability that is defective given that is from this maker is 0.03. It's 0.03, right? Because it's 3%. The probability that is defective given that comes from media supply is equal to what? is defective given that it comes from media supply? 0.02, right? We have the probability that is from this maker is equal to 0.62, and the probability that came from media supply is equal to what? 0.38. So these are the events that are mutually exclusive and collectively excess. That is what the problem is telling me. Now, they said a randomly selected DVD is found to be defective. So, they want to know what is the probability given that it's defective. A randomly is found to be defective. Use Bayes' theorem to determine the probability that the DVD came from this maker. So, they want to know this, exactly this. That came from this maker, given that I found that is defective. Okay? I know this one. What is the probability that is defective given that came from this maker? But I don't know what is the probability that it came from this maker given that it's defective. Okay? So, as you can see, the posterior probability is nothing but the inverse of the prior probability. And we want to know that, so we use the Bayes' theorem. So again, let me develop the tree diagram. This came either from two suppliers, right? This maker and what was the other? Media supply, okay? And the probabilities are pretty easy, 0.62 and 0.38. So when you add them all, you get 1.0. Now, if it came from this maker, either they are defective or non-defective. The probability that is defective, given that came from this maker, is 0.03. The same thing happened here. It's either defective or non-defective. When it came from media supply, the probability is 0.02. It means that this branch over here is 0.97 and this branch over here is 0.98. And at the end, if you add all the probabilities, conjoint probabilities, add up to be equal to 1. Okay? But what I'm interested is in the defective branches. So I know it's defective because I got the randomly selected this and it was defective. So I just want to know if it's, what is the probability that, given that it's defective, came from this maker, from this particular supplier, from this maker supplier. Right? So, based on that, the probability that it was this maker given that is defective is the probability that came from this maker times the probability that is defective given that came from this maker divided by this same probability plus the probability that came from the other supplier, MS, times the probability that is defective given that came from MS. Okay, that's a Bayes' theorem. So, what is the probability that it came from DM and times the probability that it's defective given that it came from DM is 0.03 times 0.62 is equal to 0.0186. Okay? what is this probability? The probability that it came from MS times the probability that it's defective given that came from MS is 0.38 times 0.02. It is 0.0076. Am I right? Right? 0.38 times 0.02. 0.0076. Okay? Right? So that is equal to 0.0186 divided by 0.0186 plus 0.0076, and that is equal to 0.70. So that is the correct answer, 0.71. So the probability that given that it's effective, the probability that came from supplier this maker is equal to 0.71. Because of what? Because we use the Bayes theorem. Right? So it's just a formula. You use that formula. We have the I's that are independent, mutually exclusive, no, not independent, mutually exclusive and collectively exhaustive.
When do you have to use the
The what?
in the first here, or the first formula you put up there? You know, when you had after the bottom part, it had probability of A given B at the end.
Oh, when you have many events, when you have, right now we have two events, either come from the supplier or the other supplier. But if we have three suppliers, we would have three terms in the bottom.
And then you have to have the N.
Yeah, if we have DM, MS, and probably other supplier. You would have other supplier, probability of the other supplier times the probability that it is defective given that it's from the other supplier. But then these numbers has to change. These 0.62 and 0.38 have to change because when you have these events, all these three events has to be mutually exclusive. So it has to add 1.2. So we may have three suppliers, right? And then instead of 0.62, it would be 0.5, 0.3, and 0.2. Something like that. Because these are the only three suppliers. In the case that we have three suppliers, then we would have another term in the denominator of the equation.
So when you have another term,
Yes.
you have to put in there the probability of.
Yeah, you have to have the probability that came from the other suppliers times the probability that is defective given that came from the other supplier.
But then you would have to put the one with the N in
Which end?
it.
Oh, yes, this would be the third. The n would be 3. Because the n is the number of mutually exclusive events that start at the end, at the beginning.
But you have to add that into the bottom.
No. You have to have until the number of first events. Okay? So it really depends how many. As I said before, the ethnicity, it has 5 branches. So you would have 5 branches, 5 terms in the denominator at the end when you use the Bayes theorem. Okay?